In this section, we will examine how we can make the antenna element model more realistic so that our phased array architecture represents close to reality. Let's take the case of a 64 element phased array arrangement with elements, each one of these elements modeled as isotropic. Isotropic is the easiest and quickest to assume as and also a good first order approximation for a antenna model. We specify the element pattern in the array antenna model, and we can select different types of models for the elements, and then in the first case we select isotropic. With this, if we simulate and if we plot the beam pattern, it will be like this. As you can see, all of the elements are identical. They're all isotropic, and isotropic pattern itself is symmetric. So we can see the overall far field pattern pretty symmetric, and this looks pretty intuitively pleasing. But in reality, there are no isotropic elements. Isotropic element is a purely theoretical concept. So we need to use a more realistic antenna element model. Using the other choices that we have in the tool, we can go ahead and then select a directional antenna pattern, analytically derived antenna pattern, which is a cosine antenna. We have the ability to modify the exponent to control the shape of the beam, or we can go and then select a pattern file. A pattern file that is measured for the antenna element in an anechoic chamber, or that is simulated using any of the popular electromagnetic simulation tools. In here, we have the ability to bring the pattern file simulated in electromagnetic professional platform from Keysight Technologies, or from HFSS, from ANSYS Corporation, or from MicroStudio from CST. In this case, we have a file, the file representing the simulation of a microstrip patch antenna, and we simulated that element, brought the file, far field pattern file here, and then we are going to use that as the element. With that arrangement, if we go and then simulate, we will see that the pattern is different from the one obtained previously. If we go and see, now you see the pattern is not that symmetric because each element itself is not very symmetric, does not have a symmetric pattern. And then this is different from the isotropic. So this will represent a much better and much closer to the reality. Now, is this all that we have to do for an element model? No, we have other choices and then other realism that we can bring for the antenna element model. Those aspects are, number one aspect is the question: are all the element pattern files, all the elements, are they identical as placed in a phased array architecture configuration? What I mean by that is, if you look at the configuration, we said all the element patterns in the previous simulation, we said all the element pattern files are identical. But that is not so, because if you take this kind of an arrangement and actually simulate in an electromagnetic tool, and if you simulate the pattern file for one element, so you excited this element and did not excite any of the other elements, then this will be different from the pattern file simulated for this in an isolation if there were no other elements surrounding it. Because of the proximity of the metal of the other elements, this will have a different pattern file compared to what it would be if it is in isolated state. Same thing happens for other elements. So each one of these elements, for example, this element probably see the same environment as this element, but this element will not see the same environment as the central elements. This will see a different environment. The edge elements will see even more dramatically different environment. So the element pattern file as placed in an array for each one of these elements is going to be different. It probably is okay. Some of these central elements will have the same element pattern files, almost close, so that we can make them as identical. And so the edge elements will be different depending on their position. So if we take that into account, we can do that by going into the model, and then if we select, instead of saying same for all elements, we can say individual element pattern files. Yes, that means every element pattern file is assumed to be different from the other element pattern file. So we can supply 64 element pattern files, and then this tool will take it and then simulate. In order to make that a little bit more efficient, we also have another choice of what we call custom. If you select a custom, and then we can put a file map here, and we can say which of the files are identical, which of the files are not identical by mapping here, so that it will understand the files that are that means if I want to use for all the central elements the same file, I can do a mapping appropriately for that, and that will improve the efficiency. This is the immediate aspect, a macroscopic aspect of bringing a closer reality for the phased array. Now, the other things that about the antenna in a phased array are when we have these elements in this arrangement, if we want to specify the input impedance of this antenna element, what do? Either we go in an electromagnetic simulation tool, we simulate the reflection coefficient of this, and or in a network analyzer, we go and then excite this element, and then we find its impedance, reflection coefficient or impedance. But in reality, the phased array, all the elements in a phased array, all the elements are excited simultaneously. If they are excited simultaneously, what happens is, let's say we excited all of them, and then we are measuring the reflected energy at the input of this antenna due to mismatch. The energy that we are measuring coming back at the input is not only because of the reflection due to mismatches, but also because of the energy that this picked up from the other radiators in the surrounding. So we have an impedance that depends on how the coupling, the nature of coupling from other elements coming into this antenna element. If we have that kind of a active reflection coefficient matrix, then we can easily account for the more reality of the antenna here. So we can do that in the model here, and we can go in and then say we have active reflection coefficient for each one of these elements. If we have that data, we can bring it and then plug it in, and then the simulation takes that into account. If we don't have the data, if you have an S parameter file measured on the entire array, then we can bring that as well, and we can compute from that, derive from that the impedance and the coupling. Or if you have only a coupling matrix, how the energy is getting coupled from one element to the other, we can even bring that. What we mean by ideal coupling here is that you can model it analytically, or you can bring it a measured one. Either way, it is possible, but ideal in this sense is we are making an analytical model for that. Or there is an approximate way of specifying is to derive the active reflection coefficient from the element pattern file that we provided. In either case, if we provide any of these methods, the antenna element represents much closer to what it is in reality, and we should get a pattern that represents much closer to reality. SystemVue by nature is an excellent RF simulator as well. So when we specify the active reflection coefficients on these antenna elements, if there is a mismatch between the amplifier and the antenna element, that will also be reflected in the far field simulation. The other aspect about phased array is that if we have, in this case, we have 64 amplifiers, 64 digital programmable attenuators, 64 phase shifters, and 64 antenna elements, of course. So in order to minimize the side lobes, we may put a taper on the digital attenuator. So that taper will excite each one of these amplifiers differently. When that happens, the output impedance of each one of those 64 amplifiers is different. Because of that impedance being different, they match differently with each one of these elements. The elements themselves can have different impedances, and the impedance of each one of these elements also depends on the direction of the beam. Now, this all might look very complex, but we can model all this in SystemVue as long as we have the data for the antenna elements, the active impedance or active reflection coefficient as a function of scan angle. We will be able to bring that into this model and then simulate all this in a more realistic fashion. Thank you very much.